Can you imagine never being able to play a sport again? How about never being able to play them growing up? There are thousands of people living with disabilities that make sport inaccessible to them. My name is Muhammad Ansari, and my summer project focused on closing these boundaries. Adaptive sports have proved to overcome this issue by providing accommodations which allow those with disabilities to participate. Some of these sports include adaptive hockey, and one that is of interest to us, bocce. Bocce is a sport similar to curling, where users throw a ball and get as close as they can to a target. They can physically throw the ball or have a ramp, where they can have an assistant move the ramp around to a direction of their choice. However, no option exists for those with more complicated issues, such as speech impediments. Brain-computer interfaces, or BCIs, can help overcome this. When your brain does anything, it creates signals specific to that task. A BCI can be trained to recognize signals through machine learning and then process it to the activity trying to be done. This can cause changes through visual feedback, or in our case, the movement of the bocce ramp. BCIs allow users to be autonomous and independent, serving as a novel way to overcome the problem at hand. This brings me to my project. The objectives of my project are to develop a bocce ramp that's equipped with safety features and to further develop the connection between the BCI and the ramp, allowing the user to move the ramp themselves. The methodology of this project consists in three domains: hardware, software, and firmware. From the hardware side, it was important that the ramp was both safe to operate but further mechanically functional. Movements that were of interest to us were rotation, elevation, inclination, and the release of the ball. While an initial prototype of the ramp was present, a lot of changes were needed to make sure that it kept the user and the device safe from harm. These were the release mechanism, elevation mechanism, and the rotation safety mechanism. The rotation safety mechanism was the most critical of all these three, because it made sure the ramp would not tip over and hurt the user. There's currently wiring behind the ramp, and making sure that it doesn't over-rotate was very critical. I constructed the following design, which consists of an adjustable slot mechanism as well as optical sensors. The slot mechanism serves to set the bounds for the ramp, and the optical sensors ensure that the ramp does not exceed those bounds. The next domain of the methodology was the firmware side. Firmware is the main means through which the ramp is controlled. This includes the electronics, the code that drives motion, and other parts that relate to the wiring. We utilize an Arduino Mega as well as an A4988 stepper motor to drive and facilitate the movement of different parts. A lot of firmware work was done through programming scripts, and the main thing to keep in mind when designing these is safety. Safety is critical to both the user and the device. When it came to the implementation of relevant scripts, despite the ramp having different scripts as well as the user having their own scripts, these scripts were both tied together because their functionality was so similar. For example, the interrupt service routine mainly serves to stop the ramp at the right moment so it doesn't exceed those bounds. However, this also led to the user being protected as well because the ramp would not tip over if it didn't exceed those bounds either. The last domain in our methodology was software. Software is the most upstream of all these processes, being involved in taking the user input and converting into relevant commands. The BCI algorithm would take in the input, send these commands to Unity, which would control a virtual ramp, and these virtual commands would actually lead to the real ramp moving as well. So here's our virtual ramp. The user would focus on one of the three buttons, and then from there, they'd be able to conduct different motions. This would cause this ramp to move, which would cause the ramp in real life to move as well. So here are the results. So as you can see in the following video, I'm using the BCI headset to receive my signals and convert to movement in the ramp. The BCI paradigm we use for this is an algorithm called P300, which basically has a lot of flashing lights, and you have to focus on the ones which are landing on the button you want to press. I was able to move the ramp with the command provided, and we did two preliminary trials and observed that with a rest time of 0.1 seconds and a flash time of 0.05 seconds, the accuracy was lower than when these both commands were increased. So as you can see here, I'm currently operating the ramp, and I'm able to release the ball on command. Discussing our results, it can be seen that the ramp is operational and safe for use for the user, and the device does not incur damage either. To comment on the P300 result, we found that this lower the rates of flash are, which basically means that the flash lasts for a longer amount of time, and the longer rest times there are, which is a gap between the flashes, there's a better signal. This might be attributed to the fact that the user can more easily track their flashes and focus on them as well. To conclude, this work focused on improving a prototype by implementing safety features and design features. Future work will be focused on clinical application of this device. Thank you.